So in this lecture, or in this video, what we're going to look at is first exercise in the lecture slides on how we can apply the knowledge of building up a stiffness matrix and work out the forces and the displacements on a system. So the first exercise we're going to look at is shown in this diagram, where we have 3 blocks with mass m, 2m, and 3m. They are linked together by 5 springs. Okay, so this exercise requires us to use the stiffness method procedure of the finite element analysis to determine the nodal displacement. Okay, so here we have 1, 2, 3, 4, 5 nodes. Okay, there are 2 nodes fixed to the bottom of the floor, but they are all considered as linked together. So the hint here is they are all numbered with this hash key. So 1, 2, 3, 4, 5 nodes. We want to work out the nodal displacements, and also what are the corresponding forces on each one of these nodes. Okay, it is also given that the stiffness of the elements, or stiffness of all the springs, A, B, C, D, and E, are K, 0.6K, 0.08K, 2K, and 1.2K respectively. Okay, so throughout this exercise, I will show you a sort of a trick to allow you work out the stiffness matrix faster. Okay, for simple cases like this. Okay, so we know that the force is related to the stiffness matrix K bar times the displacement on each node. So F is a column vector, K is a matrix. In this case, it will be a 5 by 5 matrix because we have 5 nodes, and then U will be the vector that corresponding to the deformation at each node. So F is forces on the nodes, K bar is the stiffness matrix, U is the nodal displacement. Okay, and we know that there are 5 nodes because there are 5 hash keys here on this diagram. We also have some variable that we know that's basically the nodal forces on 2, 3, and 4, because we know the mass of each block, which is basically the gravity that will pull this mass downwards. So on node number 2, we have mg, the mass of this block, which will, for short, we'll keep it as P. On the third node, we will have 2P because the mass is doubled, and on node number 4, we will have 3P, right, because the mass is tripled. And we also know that from this diagram, because node 1 and node 5 are fixed to the top ceiling and the bottom floor, the nodal displacement at these 2 nodes will be 0. So if you fill up the matrix equation here, we know that we have known variable that's P and U2, 0 and 0 for U1 and U5. That leaves us with 5 unknown variable. F1, the force on node number 1, that should be F5, which is written here. The force on node number 5, so F1, F5, there's a mistake here, so F1, F5, F1, F5. And the displacement on node 2, 3, and 4. So U2, U3, and U4. Okay? Be careful, don't get confused with this 1M, 2M, and 3M. There is node 2, node 3, and node 4. So we have U2, U3, and U4. And the forces are linked to the nodal displacement by the stiffness matrix K bar. So we need to work out what this K bar is, right? Now, the trick to write down this K bar is to first write down this 5 by 5 block of the matrix. And in this case, we will have the nodes being coupled together by some elements, some springs, okay? Now, this is very common in many physics problems, as I mentioned a couple of times. For matrix, you will first have the diagonal matrix element, right? That goes 1, 1, 2, 2, 3, 3, etc. in this case. Now the matrix, the diagonal matrix element in this case, or in many of similar cases, will be the sum of the spring constant that is linked to that node. So to check that, you see node number 1, you only have one spring linked to it, so it's A, which is correct, right? On node number 2, you have A and B that's linked to node number 2, so it's A plus B. On node number 3, you have 3 spring that's linked together, B, C, and D. So the matrix element is B plus C plus D. Okay, so that gives you all the diagonal matrix elements in this stiffness matrix K bar. For the non-diagonal element or the off-diagonal element, okay, if it connects two nodes that are linked by a spring, then the value is the negative of the spring constant. If the two nodes are not connected anyhow, then you give a value of 0. So to check that, you see, for example, this matrix element linked together nodes 1 and 2. Nodes 1 and 2 that are linked together is minus A. Right? The spring constant is A, so this matrix element here is minus A. Now, because this matrix is a diagonal matrix, so you will have, by symmetry, the other side of this matrix will also have minus A for the element that couples 2 to 1, right? 1 to 2, and 2 to 1. Right. And so on and so forth. The tricky bit is probably the node number 4 here, which you will see, for example, node 4 is coupled to both node 3 and node 5, so you will have 3, 4, which is minus C here. And also you will have 4 and 5, which is 4 and 5 here is minus E. So that's how we build up this stiffness matrix element quickly, right? Now the next step is quite trivial. All we do is basically put in the value of the matrix spring constant or the stiffness elements into this matrix. So that gives me this big block of numbers. And what you're going to do is essentially plug this matrix back into this equation. And that gives us 5 linear equations with 5 unknown variables, which we can solve. Right? If you forgot how to solve the matrix equations with linear algebra, you can always solve these equations using substitution. Now, how to solve this particular case, for example, in this case, I can work out what U4 is in terms of U3 and P from equations number 4, and then substitute it back to the third equations. That basically eliminate U4 in the third equations, which only left 2 unknown variables, U2 and U3. When that happens, I can solve equation 2 and 3 together to get the answer for U2 and U3. Okay, so once we solve U2 and U3, that allows me to solve F1 from equation 1 as well as F5 from equation 5. And the solution is basically written here. Okay, as you can see, the numbers are pretty awful, but in most of the exercise we are doing, we will only be requiring you to write down this stiffness matrix, the stiffness matrix, rather than actually solving them. Okay, so being able to write down the matrix is actually the most important part of this exercise.